Hello, welcome to today's class. This is our second class on latches. In the previous class, we talked about the basic SR latch using NOR gates, and this is how the logic circuit looks like for a basic SR latch using NOR gates. And in the last class, we saw that this was the characteristic table for the circuit. And what we saw is that when both the S and R inputs are 0, then the state of the latch do not change. So if QA was 0, it remains to be 0, and if QA is 1, it remains to be 1. And when the input is S equal to 0, R equal to 1, and the latch goes to the reset state. And what we mean by reset state is that the QA input becomes equal to 0. And when the S and R inputs are equal to 1 and 0 respectively, the latch goes to the set state. And what we mean by the set state is that QA output will be equal to 1. Then we also saw that when we give both the S and R inputs to be equal to 1, then both the QA and QB outputs become equal to 0, 0. And since QA and QB should be the complement of each other, we said that S equal to 1 and R equal to 1 is, we should not use this input because it takes the latch to invalid state. And we also saw that when we change from S equal to 1 and R equal to 1 to S equal to 0 and R equal to 0, so at the same time, if we change both the inputs from 1 to 0, then our latch may go into oscillation. And oscillation, the state will keep toggling between 0 and 1, and the latch will not go into a stable state. However, in a practical scenario, one of the feedback path may have a slightly smaller delay than the other, and what we said is an infinite sequence of toggling that would not happen in a real life situation, and the latch would settle to a stable state, but we wouldn't know in which state the latch would settle to, whether 0 or 1. So we say that the state of the latch will be indeterminate, and hence this input S equal to 1 and R equal to 1 we should avoid. We call it a invalid input. So in the previous class we looked in detail how the state of the latch changes when we change the input. In today's class we will build upon what we discussed in the previous class, and I will not show in a greater detail about how the state of the latch changes as we change the input. With the knowledge from previous class, I hope you will be able to validate what we will be demonstrating in today's class. Okay, so this was the characteristic table for the basic SR latch using NOR gate, and this same table we can represent it in a slightly different way, and it is shown here. So as you can see, we still have the S and R column, but now we have a column called QT plus 1. So QT plus 1 is actually, it signifies the next state. So at time t plus 1, what is the state? That is called QT plus 1. So Qt plus 1 will tell you what's the value of QA is at time t plus 1. And then, so that was the next state, and qt is our current state. So at time t, what is the value of qa? That we call is qt, and we call it the current state. And as we change the input, the state of the latch will change, and that would be our next state, which is qt plus 1. So what is the time, what is the state at time t, and what is the, and once we change the inputs, what will be the state at time t plus 1? So qt is the current state and qt plus 1 is the next state. And since, as we studied in the previous class, when we change the input to 0 0, then the state do not change. So if s input is equal to 0 and r input equal to 0, if no changes takes place, that means our next state will be equal to the current state. So qt plus 1 will be equal to qt. So that's why we write qt here. Because s equal to 0 and r equal to 0, we studied in the last class, s equal to 0, r equal to 0, there will be no change in the state. If there is no change in the state, then our next state, which is qt plus 1, will be equal to our current state, which is qt. So for s equal to 0, r equal to 0, qt plus 1 will be equal to qt. That's what the first row signifies. When we change the input to s equal to 0, r equal to 1, qt plus 1, our next state will be equal to 0. That's our reset state. And when we change the input to s equal to 1 and r equal to 0, our next state, in the next state, q will be equal to 1. So qt plus 1 will be equal to 1, and that is called the set state. And s equal to 1 and r equal to 1 was a invalid state, invalid input, as we had discussed in detail in the last class. So this is a new way of writing the characteristic table, and this is the format we will use in the preceding slides. Now here is a basic SR latch using NAND gate. So instead of NOR gate, we are now using NAND gate, and we call this output Q and Q prime. But now the position of the two inputs are interchanged. If you look at the basic SR latch using NOR gate, then R is connected to the NOR gate whose output we call Q, and S is connected to the NOR gate whose output we call Q prime. So R is connected to the NOR gate whose output is Q, and S is connected to the NOR gate whose output is Q prime. But now when we are implementing the basic SR latch using NAND gate, we have changed the position of the two inputs. Now we are calling this input as the S input. So the NAND gate whose output is Q, we connect S input to that NAND gate, and the NAND gate whose output is Q prime, we connect the R input to that. So we have interchanged the position of the two inputs. And now if you work out like we did in the previous class, you would see that this would be the characteristic table for this logic circuit. And this characteristic is just the inverse of the characteristic table for basic SR latch using NOR gate. So for NOR gate, 1 1 was the invalid state and 0 0 was no change state, but now it's the reverse. 1 1 is the no change input and 0 0 is the invalid input. And for NOR gate, S equal to 0, R equal to 1 was your takes the latch to the reset state, and S equal to 1, R equal to 0 takes the latch to the set state. Again, it's just the inverse here. We go to the set state when S is equal to 0, and we go to the reset state when R is 0. So this particular characteristic table is just the inverse of what we had here. So remember this fact, and remember that the position of these two inputs has been changed. Now let us look at gated SR latch using NOR gates. So this is the logic circuit for the gated SR latch using NOR gate. So here we have the basic SR latch, and to that we connect two AND gates. We have a clock input. The clock input is connected to both the AND gate, and for one AND gate the input is R, and for the other AND gate the input is S. Now let's look at the behavior of this logic circuit. So when we make the clock input equal to 0, both this AND gate, one of the input will be 0. So for this AND gate, one of the input will be 0. For the other AND gate, one of the input will be 0. And we know that whenever one of the input to a AND gate is 0, the output of the AND gate will be 0. So output of both the AND gate will be 0. Doesn't matter what the value of R and S is. When clock input is 0, output of both the AND gate will be 0. So now these two inputs to the basic SR latch are 0. So if we consider only the basic SR latch, so we have both the inputs 0, which means there will be no change to the state. So what do we see? We see that when the clock input is 0, no change will take place in the state of the latch. Doesn't matter what the value of R and S is. Now if we make clock input equal to 1, then the output of the AND gate will depend on what the value of R and S is. If we consider R to be 1, then output of the first AND gate will be 1. And if we consider S to be 0, the output of the second AND gate will be 0. So when the clock input is 1, the output of the AND gate will depend on what the value of R and S is. In this particular scenario where R is 1 and S is equal to 0, the output of the AND gate, first AND gate will be 1, the output of the second AND gate will be 0. So now we have a situation where for the basic SR latch, the R input is 1 and the S input is 0. So we know from the characteristic table of the basic SR latch using NOR gate that Q will be equal to 0, which means we go to the reset state. So what do we see? When clock input is 1 and R input is 1 and S input is 0, the latch will go to the reset state. Similarly, if you work it out yourself, you will see that if we put R input equal to 0 and S input is equal to 1, then the latch will go to the set state. And if we make both R equal to 1 and S equal to 1, both these outputs will be equal to 1, which means that would be invalid input. So with this discussion, we can say that the characteristic table for the gated SR latch using NOR gate would be this table shown here. The table shows that when clock input is 0, it doesn't matter what the value of S and R input is. Our next state will be equal to the current state, which means no change will take place. Also, when the clock input is 1 and both S and R input are 0, again our next state will be equal to the current state and no changes will take place. When clock input is 1, S input is 0 and R input is 1, we will go to the reset state. So our next state, which is Qt plus 1, will be equal to 0. And if clock input is 1, S input is 1 and R input is 0, our next state will be equal to 1. So the latch will go to the set state. And if clock input is 1, S input is 1, R input is 1, that would be invalid input. So this is the characteristic table for the gated SR latch using NOR gates. And here is the symbol for the gated SR latch using NOR gate. So if you want to use the gated SR latch in your logic circuit, in a bigger logic circuit that you want to build, if you want to use the gated SR latch, this is the graphical symbol for the gated SR latch. Here is a timing diagram and that shows the clock input, the R input and the S input. So given these three signals, clock, R and S, you can find out how the Q and Q prime output would look like. To draw the Q and Q prime signal given this other three signal, you have to remember the characteristic table, and from the characteristic table you know that the state of the latch will change only when the clock input is equal to 1. So clock input is 1 during this time, the clock input is 1 during this time, the clock input is 1 during this time and this time and this time and so on. At the other time the clock input is 0. So when the clock input is 0, it doesn't matter what happens to the R and S signal, your Q and Q prime will not change. Let us look at the first time that the clock input is changing. During this time the clock input is 0, the S input is 0, the R input is 0 and S input is 1, and we assume that at the start the Q output is 0 and hence the Q prime output is 1. So now at this time when the clock input is going to 1, your R input is 0, S input is 1, so the latch will go to the set state, which means Q output will become equal to 1. So Q output is changing to 1, which is Q prime is changing to 0. Now at this point the clock input changes to 0. So even if at this point R is changing to 1 and S is already 0, but still your Q output will not go to the reset state at this point. When R is going to 1, we don't see any change to Q. That's because clock is 0. At this point when clock is 1, at the time R is 1 and S is 0, so we will go to the reset state and hence Q is changing to 0 and Q prime is changing to 1. Same thing, once that change happen, then clock goes to 0, and when clock is 0 we see some changes in R and S, but that would not affect the Q and Q prime. There will be no change in Q and Q prime during this time when the clock is 0, but then when clock is going high again, at that time R is 0 and S is 0. Since both R and S is 0, again there will be no change, because clock equal to 1, R equal to 0, S equal to 0 means no change. If you go back to the characteristic table, you will see that clock 1, R0, S0, then no changes will happen. Hence Q was 0, it remains 0, no changes takes place there. And similarly Q prime was 1, it remains 1. Then clock input goes to 0. So again, even if R and S will change, that would not affect Q and Q prime, because clock is 0. Now clock goes to 1 at this point of time, and at that time your R input is 0 and S input is 1, which means the latch will go to the set state because S is 1 and R is 0. Set state means Q will change to 1. So it was 0, it will go to 1, and Q prime was 1, it will go to 0. And then again at this point the clock changes to 0, so no further changes will take place. No further changes will take place because clock is 0. Even if R and S changes, there will be no change, and that's what we see, and there is no change in Q and Q prime. And then at this point clock goes high again, and at that point R is 1 and S is 1, so both the output Q and Q prime will become 0 0. Remember that we discussed in the previous class, when R and S both inputs are 1, your both Q and Q prime will become equal to 0. So that's what we see here. And now clock goes to 0. As soon as clock goes to 0, remember both the inputs to the basic SR will become 0 0 0. So both the inputs are 1, and then it changes to both the inputs as 0. So our latch will go into oscillation, and we will not be able to tell at what state the latch will settle. So it's an indeterminate state. It will go into oscillation here. So that explains this timing diagram. And now let us move on to the next circuit, which is the gated SR latch using NAND gate. So again we have the basic SR latch using NAND gate this time, and to this basic SR latch using NAND gate we connect two NAND gates, slightly different from what we did for gated SR latch using NOR gates. So we have two NAND gates here. We connect the clock input to one of the NAND gate and the clock input to the other NAND gate, and S input we connect to one of the NAND gate, and R input we connect to the other NAND gate. And remember, this Q output, to that we connect the S input, and to Q prime we connect the R input. Now if you look at the behavior of this logic circuit, if the clock input is 0, then the output of both these NAND gate will be equal to 1. It doesn't matter what the value of S and R is. As soon as the clock input is 0, the output of both the NAND gate will be 1. So now we have a situation where both the inputs to the basic SR latch using the NAND gate are 1. And if you remember a few slides back, when we studied the characteristic table for the basic SR latch using NAND gate, we saw that both the inputs equal to 1 signify that no change will take place. It is opposite. The basic SR latch using NAND gate is like the opposite of the basic SR latch using NOR gate. So for NOR gate 0 0 signify no change. For NAND gate 1 1 signify no change. So what we see here is when the clock input is 0, no changes will take place. When clock input is 1, the output of the NAND gate will depend on what the value of S and R is. If you consider S to be equal to 1, then the output of the first NAND gate will be equal to 0. And if you consider R input to be 0, the output of the second NAND gate will be 1. So we have a situation where the two inputs to the basic SR latch using NAND gates is 0 and 1 respectively. And if you remember, This is your S input and this is your R input in the basic SR latch using NAND gate. So S input equal to 0 and R input equal to 1 signify that we will go to the set state. Again, it's just the opposite of the basic SR latch using NOR gate. In NOR gate, when S is equal to 1, R is equal to 0, we go to the set state. But in case of basic SR latch using NAND gate, when S is 0, R is equal to 1, we will go to the set state. And since we go to the set state, Q will be equal to 1. So we are in the set state. So what we see, when clock input is 1, the S input is equal to 1 and R input is equal to 0, your Q output will become equal to 1. And similarly, if you try it out, if you make S equal to 0, R equal to 1, you will see that we will go to the reset state. So now what we see is that although the basic SR latch using NOR gate and the basic SR latch using NAND gate had the opposite behavior, the gated SR latch using NOR gate and the gated SR latch using NAND gate has the same characteristic table. They are no longer opposite. So for the gated SR latch using NAND gate, this characteristic table is exactly the same as gated SR latch using NOR gate. And what I mean is that when the clock input is 0, no changes will take place. When clock input is 1, the S input is 0, R input is 0, there will be no change. When clock input is 1, the S input is 0 and R input is 1, we will go to the reset state. So now we are going to reset state when S equal to 0 and R equal to 1. In case of basic SR latch, is the NOR gate and the NAND gate implementations are opposite, but in case of gated SR latch, both the NOR gate and the NAND gate implementation is the same. So when R is equal to 1, S is equal to 0, we go to the reset state, and when clock is equal to 1, S is equal to 1 and R is equal to 0, we go to the set state. And clock equal to 1, S equal to 1 and R equal to 1, the output will not be, this is an invalid state input. So this is the characteristic table for the gated SR latch using NAND gate. Now we'll talk about gated D latch. So this is the logic circuit for a gated D latch. And what we see is, let's look at this behavior. So when we make the clock input equal to 0, then the output of these two NAND gate will be 1. Output of both the NAND gate will be equal to 1. So now we have a situation where we have a basic SR latch implemented using NAND gate, and both the inputs to this basic SR latch using NAND gate is 1, and hence there will be no change to the state. So this comes from the characteristic table for the basic SR latch using the NAND gate. For basic SR latch using NAND gate, input, both the input equal to 1 signify no change. So what we see is that when the clock input is 0, no changes will take place in the gated D latch. When the clock input is 1 and the D input is 0, then the output of the first NAND gate will be, okay, before that, if the D input is 0, then this input to the first NAND gate will be 0. And since the input to the second NAND gate is the complement of D, and D is equal to 0, this input to the second NAND gate will be equal to 1. Hence, the output of the first NAND gate will be 1, because one input is 0, the other input is 1, and hence the output of the NAND gate will be 1. And for the second NAND gate, one input is 1, the other input is also 1, and hence the output of the NAND gate will be 0. So now we have a situation where the S input is equal to 1 and R input is equal to 0 in a basic SR-Latch using NAND gate. So and we know that when R is equal to 0 and S equal to 1, the latch will go to the reset state, which means Q will be equal to 0. So what do we see? When clock is 1 and D is 0, your Q output will be equal to 0. Let's see what will happen for D input equal to 1. When D input is equal to 1, the S input will be equal to 1 and your R will be equal to 0 because R is the complement of D. And now the output of the first NAND gate will be 0 because both the inputs to this NAND gate is 1, whereas the output of the second NAND gate will be 1 because one of the input is 0, so the output of the NAND gate will be 1, and hence we have a situation where the S input is 0 and the R input is 1, and this input combination signify that the basic SR-Latch using NAND gate will go to the set state, which means Q will be equal to 1. So what we saw is when clock input is 1 and D input is 1, the Q output will be equal to 1. And hence we can show the characteristic table for the D latch to be as shown in this table. So when clock input is 0, it doesn't matter what the value of D input is, our next state will be equal to the current state, which means no change will take place in the latch. When clock input is 0, no change will take place. But when clock input is 1 and D input is 0, your next state will be equal to 0. And when clock input is 1 and D input is 1, your next state will be equal to 1. So when clock is equal to 1, your next state will be exactly the same as the D input. So your circuit becomes transparent in the sense that when clock input is 1, whatever input you have at D, that will appear at Q. If D is 0, Q will be equal to 0. If D is 1, Q will be equal to 1. And now since we have only one input in this logic circuit, we have the clock input and then another input D. We will now never have the input combination which will make the basic SR-Latch go into a indeterminate state. For the basic SR-Latch, we will never have a situation where both the inputs are equal to 0, 0. That's because we are now using only one D input, and that's the input we connect as directly, and we take the complement of the D input and connect it as the R input. So the situation will never occur where the latch will go into oscillation. Okay, so this is all that I have for today's class. Before we end, let's look at a timing diagram for gated SR-Latch. Of course, this is the graphical symbol. If you want to use the D latch in your bigger logic circuit that you want to construct, this is the symbol you should use. And here is the timing diagram. So again, the timing diagram shows the two input signals, clock and D. And given these two signals, you need to calculate the Q signal. And based on your understanding of the characteristic table of the D latch, you can easily construct the Q output. So before time t1, your clock was 0 and D was 1, and we assume that Q was 0. So we are assuming that at the starting Q is equal to 0. Now at time t1, clock changes to 1. So when clock changes to 1, your Q output will be exactly the same as the D input. So since D input is 1, Q will become equal to 1. It was 0, so it will change to 1 because D input is 1. and for the whole duration D input is 1, so Q will also remain 1. Now at this point clock changes to 0. So when clock changes to 0, from that point onward there will be no change in the Q output up to the point where clock again goes back to 1. So from this point up to T2 there will be no change in the Q output even if D changes. So here D is changing from 1 to 0, but we don't see Q changing. That's because clock input is 0. The clock input becomes 1 again at time T2. So at time T2 we'll see that Q is changing from 1 to 0. That's because at time T2 D is equal to 0. So whatever is the value of D, that would be the value of Q when clock is 1, and hence clock Q is changing to 0. For this duration the D do not change anymore, so there is no further change in Q, and then after this point the clock changes to 0 and remains 0 up to T3. So even if D changes, there won't be any change in the Q. At T3 clock is changing to 1, and at that point D input is 1, so Q is changing to 1. And then when clock is 1, the D input again changes to 0. So since clock input is 1, Q will also change to 0. As soon as D changes to 0, Q is also changing to 0. And then D remains 0 for the next point up to this point of time. So Q also remains 0. And then clock becomes 0. And now even if D changes, there will be no change in Q because clock is 0. At T4 clock changes to 1, and at that point D is 0, so Q will also be 0, and Q is already 0, so it will remain 0, so no changes takes place in Q. And then when clock is high, we see that D is changing to 1, so at the same time Q will also change to 1. And that's what the timing diagram looks like. So if I change the D input to another signal, based on your understanding, you will be able to construct the output Q signal based on the D input signal. So this is all that I have for today's class. We'll meet again in the next class. Thank you. Bye.